Okay, hello everyone, and welcome to today's webinar, which will be on electrothermal co-simulation of 3D-IC structures. And we're going to cover, our speaker will cover today an introduction to what 3D-IC structures are all about, and then show us an example of analyzing one of those structures. And as you have questions, you can type them into the chat window at the bottom of your screen. So that little icon there, just click the chat, type them in, and at the end of the webinar, we'll get to as many of those questions as we have time for. So let me introduce our speaker. Our speaker is C.T. Cao. C.T. is a product management director in our multi-physics system analysis group responsible for electrothermal analysis. His fundamental training is in mechanical engineering, but he has spent his entire career in electronics-related applications. Prior to Cadence, CT was an industry consultant in the design of MEMS devices. He also worked at Applied Materials, where he participated in the design and modeling of semiconductor manufacturing equipment. And earlier in his career, CT was a senior packaging engineer at National Semiconductor. CT received his bachelor's degree from National Taiwan University, his master's in mechanical engineering from the University of Texas at Austin, and a PhD in aeronautics and astronautics from Stanford. So CT, tell us about today's presentation.
Hi. Good morning, good afternoon, good evening, everyone. I'm more than excited to share and what we learned and what we envision on this topic. First, let's look at the well-known Moore's Law. As we all know, Moore's Law has been slowed down during the past several years, and it has been hitting the physical limit about 2 nanometer. Take, for example, 2 nanometer means about 10 layers of a tungsten atoms you can deposit on the wafer. So basically, industry and all those company there, they have rewrite their roadmap to a heterogeneous integration of the advanced packaging. Actually, during the turn of this millennium, Moore's Law has received a warning from a thermal issue. I still keep this presentation from Andy Grove because it was so shocking and inspiring at the same time. It's given about 2002. Basically, it says when we shrinking the device size, we have to keep it cool because the enormous power density will be dumped into the single little transistor, and it could go up to like rocket nozzle wall. The heat we have to remove from the rocket nozzle, or even go to the like the sun. But scientists and engineers, just like always in history, they never give up. They never say, okay, that's it. They will do whatever it takes to keep the Moore's Law keep going, especially for Intel engineer, I think. Then after the turn of this millennium, actually the curve doesn't goes up. Power density versus as the Moore's Law versus years, it actually goes down because people has it creatively do whatever engineering enhancement, improvement to tame or manage the thermal issues. But to my opinion, thermal issue will never be get rid of. So when we go into this heterogeneous integration of a packaging, thermal issue comes back again, and it becomes more critical when that lasts. So when we go the heterogeneous integration, what does it mean? It basically means we put all those multifunctional components or chips on one single platform. No matter it's an interposer or a substrate. It could be an image sensor on the chips, could be a memory, could be the RF, could be whatever functional devices a designer want to put into that systems. So we are going into this more and more age, and we're going to combine all those different functional devices on one chips. This will be an example. This slide shows an example of illustrative example of a packaging. Here we have a processor. We have multiple high bandwidth memory sitting on the interposer and the substrate. Of course, between those silicon layers, there will be interconnects. There will be dielectric to put them together. Then we heard this like system in package or system on chips and foundry, and also the packaging assembly and testing house. They are developing in parallel different solutions to enable this advanced packaging. All in all, the idea here is basically building high-rise on the chips with different thickness, different function, different power scheme, different usage, but they're all put on one platform. So you have, and the heat generated from all of them got to be dissipated out. Among all those advanced packaging flow, here is an example. Cadence has been working with an industry leader and to work with the TSMC for them among their multiple 3D-IC advanced packaging, including integrated fan-out, CoWoS, wafer on wafer, and silicon on IC. So from here, I like to jump to a demonstration to demonstrate how and what we can analyze the thermal issues on this advanced packaging 3D-IC problem. Let me share another screen. Tom, can you see this screen?
Yes.
Okay.
Yes.
Yeah. Next, I'd like to do this demonstration of a complex systems of a 3D-IC using our newly launched tool called Celsius Thermal Solver. This is a canvas. Here we already imported in the substrate, and we imported a complex interposer in an integrated fan-out package. During this demonstration, I like to focus on three aspects. First, the first aspect is geometry resolution, because we need to have the correct or complete geometry for analysis. We could, in this tool, we can import it different design from this different file format. We can import it like a BRD file, MCM file from Cadence design for package and board. And also we can import a set or step file from the typical 3D MCAD design. And all those other design, you can see we have a step function. So in this case, we are going to import several setup design to demonstrate a 3D-IC assembly. So let's import several components. Like we have this package on package. This one will be a simplified and package on package component. So let me include it one by one. So for a complex system, it could be a design already available. Then we could directly import the design with design details, like in this integrated fan-out package. And we can also import a build component. The designer just have maybe a roughly outline, an outline with like a length, width, height. And they don't have a detailed design, but it's ready to do a floor planning or for the pre-design analysis. So let's see. So here We imported all those design for this example. I have to apologize that we cannot release any customer related information. So we have like this is a MO POP, package on package, and you can see we have this markup package and HBM and integrated fan out systems. So here we like to jump to a already built up based on this one. Yeah, this is the true design. We integrated, put everything together. Integrated FinFET, integrated fan out package. We have all those design details. Then we have HBM. Here, I'd like to show you that actually those, you can see the solder balls. Those components are having different height, different shapes. So they could be or a heterogeneous assembly of this 3D IC. So that would be the first aspect. Second aspect I like to show is the we have to do electrical thermal co-simulation because as we know, the temperature affects electrical resistance, and electrical resistance together with current will introduce additional heat source as a joule heating. So in this tool, we could specify simulation type like a static or transient thermal ET co-simulation for those setup. Of course, I will not get into the detail of the setup because it's not the purpose of this webinar, but we want to specify that a electrical thermal co-simulation will be critical for a typical 3D IC configuration analysis. Then third aspect is we want to focus on the power input because when you solve the heat problem, basically it is the heat in, the heat out, and how heat is transported in between. Then for each package in the electrical thermal co-simulation, basically we could specify the power input, like for this case, we could specify power input as a grid pattern on these chips. And in this example, this chip has a 5x5 regular grid, but it could be irregular grid. And those power can come from a typical IC design tool like a Voltus or Virtuoso or Allegro or all those tools. Then the power could be uniform or changing with time. Like for instance, for this package, we could have 4x4. Different package has a different power scheme. The key things is could be those power can change with time, but that's what nowadays the designer want, because when they have a multiple functional device on one substrate, then you want maybe this chips is on this time and that chip is off, or some key component will keep heating up. So it's all changing with time. It's not a steady state problem anymore. So those three factors I've been focusing. I want the audience to take away are first, the geometry, manipulation, the geometry of resolution of the whole system. Second is we want to do electrical thermal co-simulation. Thirdly, the user are focused on the power profiling, like versus time, and we have to do transient analysis. Okay, so this will be the simple illustration on the tool of a Celsius we could do. And next, I'd like to go back to PowerPoint to show you some results. First, the geometry resolution. You can see the results for this integrated fan-out package. We can resolve every design detail, the micro bump under the die, the traces, the vias. And on the other hand, if the user designer doesn't have a true design ready, but they have a ballpark of the profile of the chips or the component or device, they can do this type of on the top. You can do this this kind of floor planning. They can move this component here to change the power with a different duty cycle or whatever they can do. They can see the effect of the overall power budgeting or power management of this whole systems. And secondly, electrical thermal co-simulation. This is just take that integrated fan-out package, for example. If thermal only, we got about 60 degrees C in this case for this simulation. But if we include ET co-simulation, where I put the current going through one trace and coming out another trace, then you can see this portion are heated up significantly to, well, almost double the temperature. Of course, as I said, the case, and we cannot show customer design, but we just want to show the capability, what we can do, including both electrical and thermal post-simulation. And thirdly, I'd like to show you this power profiling and the transient analysis. Here you can see we have set it up all those assembly with power, and like in your cell phone right now, you have standby mode, you have a burst mode, you have a different mode, and the steady state temperature may cause a over design of the device, no matter it's a cell phone or other devices, because right now the designer want to dump a large power within a short period of time, but they may want to turn off that with a suitable period of time, so they can boost up the performance of the whole systems in order to optimize the design and doesn't use a steady state temperature as a criteria. So in here, we're doing a typical transient analysis. Hope everybody can see this animation of this case. Let me see. There's something weird happening here. I'm not sure why. Let me go back to the PowerPoint view. Okay, come back. So, see? Then in this case, we play with the power input on different component. You can see, especially this POP, getting hot and cold again. So it means there's a pulse, a trend of a pulse of power dumping into this device. Then here we just want to demonstrate an example that the user could have a duty cycle of power on different components, so you could see the effect when they do the electrical thermal co-simulation. Okay, so I like to go back to where we just talked about here is first, in a tool like Celsius Thermal Solver, we can build up a assembly. Depends on the designer's requirement. We want to provide a flexibility to the designer. If the design has a detailed design of the package or HBM or their interposer, like in this interposer, it has a true design details, then they can directly import it into the tool. On the other hand, if they have some component in the 3D-IC configuration is pre-designed at the pre-designed stage, they can do the floor planning, evaluating the thermal issues, maybe changing through silicon via in between the chips, then to see if they can help dissipating the heat better. Then in that case, they can put it in to this assembly by themselves, or created a component outside using the same tool, then import it again. Then that component could be reused, could be modified, could be changed or modified to different design. So it's like playing Lego, basically. So we want to create a flexible, useful design environment, and including analysis that they could help the our customer and or the designer have better efficiency in their design, their work. Then electrical thermal co-simulation is definitely another needed because electrical thermal are interwoven together, and nowadays the heating cannot be ignored. Then we have the thermal and electrical co-simulation solver solving together by iteration to reach an equilibrium to see the hotspot change due to the joule heating, or you can modify the design to have a wider trace, fatter via, or changing the power profile locations. Then transient analysis, like I mentioned, is really a key things in many system design. So what the heat or thermal response changing with time will be a key factor for designer for the next generation chips like this 3D-IC configurations. I think I'll stop here for this like a conclusion for this webinar, then pass ball to Tom to see if I'm more than happy to discuss any question that the audience may have.
Yeah, CT sounds great. So everyone, you can ask a question by clicking the chat icon at the bottom of your WebEx window, and we already have a couple of good questions. So the first one comes from Martin, and CT, he asks, how is the co-simulation done? What is the electrical model? What is the electrical simulator? In other words, how do you get the power and the currents into Celsius?
Okay. The current or voltage could be directly specified into the Celsius. You could define a patch, a location like a pad or solder ball. You can set voltage and current. So electrical current co-simulation here, electrical thermal co-simulation here is basically coming taking the joule heating. So we are not doing like the high frequency switching like gigahertz electrical or electricity things, because for thermal, as we know, the time constant for thermal is much larger than electricals. So we have averaging mode power or current specified as the initial condition in Celsius. Then they will do iteration there.
And if people have our Voltus tool, Voltus will compute the powers and import that into Celsius, right?
That's exactly right. So we have multiple customers and multiple cases ongoing right now. Voltus can provide Celsius a power profile, like I mentioned, power profiling. Like they can discretize the chips into regular, irregular grids, and each grid, Voltus will give us uniform power in the grid or a transient power. Then Celsius can take in, then do the jobs. So traditional thermal analysis, including CFD, the power on the chip or power on the heat source got to be assumed, or could be uniform or some variation. But here we want to take the real power analysis from the IC design tool.
Yeah, and we have another question. Can we simulate electrical thermal co-simulation employing a cooling element like a fan for phase change or a phase changing liquid lines? How would you incorporate the environment, CT?
Yeah, that's a great question. That will take much more time to answer that. And yeah, for larger or macroscopic systems, you have a cooling, you have a fan. Then we have to take a divide and conquer. So because the fan cooling, there's a bigger environment, but still the heat source, we can take the power in. Then we can do several testing run to see if the overall system, including all those cooling apparatus, would they be how sensitive it will have, or how sensitive effect it will have to inside electrical thermal co-simulation. We can do multiple things to tackle that problem.
And CT, you're not showing it here, but Celsius will do a CFD analysis too, right?
Yes, of course. So we are when this webinar, we are not just trying to promoting Celsius, but Celsius do have a CFD. We have 3 application. We have IC centric, we have package board centric, and we have a system centric application. For 3D IC configuration in this webinar, I will say it will be more in the category of our IC centric application. We do have other application-centric application, not included in this webinar. Maybe later, Tom, we can have another webinar.
Yeah. So another one is, can you include a MOSFET electrothermal model like current density or VGS or the TVDS?
Well, that's a very creative and interesting, exciting question. Personally, I like to do that. But at this moment, I think in the transistor level, Celsius will rely on all those IC design tool, like we have mentioned that Voltus or other Cadence tool. People are they all know that. So we will rely on that to provide a power profiling, either static or transient, to Celsius, because Celsius is an analysis tool. But that aspect, I think we definitely could take care of that, but we will integrate with IC design tool.
Okay. Somebody asked if we can release the slides, and yes, I'll send out slides to everybody on the attendee list. Here's another one. What is your level of support to set up the right thermal coefficients for different layers and subsystem coupling? For example, depending on die thickness, mold, soldering profile, etc. Kind of a detailed question.
Is it heat transfer coefficient, I'm guessing, or heat thermal conductivity? Yes. Then, of course, the thermal material property could be imported by user or as a file. All those heat transfer related coefficients, of course, for a tool like this, we all have a build up a manual for the user to easily input, or we could have a tickle command like running on the background. If you have you can put all those information in a certain specific format, then the tool can read it in.
And this will be last question is, hello, are there model order reduction? Is it possible to generate equivalent thermal network from an FEA model?
It's definitely on our roadmap. We are, if you can see, Celsius, we have this, we have on our roadmap and is in planning, and we are doing that. And there will be a, I will say, wait and see. We'll definitely looking on that, because that will be another aspect to create a small network. It's definitely in our radar.
Okay. Well, hey, thanks, everybody. We're out of time. And if you have additional questions, please send them to me, thomas@cadence.com. Just go to the calendar invitation. It came from me, thomas@cadence.com, THOMAS@cadence.com. Email those to me. I will get them to CT, and we'll get a response back to you. So thanks, everybody, for attending. We really appreciate it, and all the best.